Okay, so now we're going to look at what else can determine whether a nucleus is going to be stable or unstable. So we've looked at binding energy, we've looked at the strong nuclei force. Now we're going to look at the relationship between the number of protons and the number of neutrons in a nucleus. Essentially, if you have too many neutrons, too many protons, it upsets the balance, so it's no longer balanced. I mean, it doesn't necessarily have to be balanced, because if we look at lithium for an example, we've got 3 protons and 4 neutrons. Okay, well, I'm going to write it down just so it reminds us of what we've got. 3 protons, 4 neutrons. It's not perfectly balanced, but in an ideal world, it's not going to cause an issue. Okay, a difference of 1 is not going to cause a huge issue. If that was a difference of, say, 10, that's when things are going to start to get a little bit dicey. That's when things are going to start to become very unbalanced and we're going to start having issues. So it has to be a distinctive difference between the two. So too many neutrons or protons will disrupt the balance, and this affects the binding energy, and it makes the nucleus unstable. So if we have too many protons or neutrons, so too many protons or neutrons, it upsets the balance. This disrupts the binding energy. And it makes the nucleus unstable. Okay, so too many protons or neutrons, it upsets the balance, it disrupts the binding energy, and then this makes the nucleus unstable. So now we look at the periodic table. We look at the relationship between the number of protons and the number of neutrons. So at the beginning of the periodic table, so low down in the periodic table, and what I mean by low down in the periodic table is anything close to the start, as in anything with a low proton number. So, you know, anything from hydrogen with 1 proton to about I'd say anything to about krypton, which has got 36. Anything kind of after that, it starts to get a little bit unstable. Still relatively stable, but it can start to get, that's when we start to see some signs of radioactivity. So low in the periodic table, low in the periodic table, the proton number is relatively equal to the neutron number. So that little scribbly line symbol means approximately. So the proton number is approximately the same as the neutron number. But if you go higher up in the periodic table, so higher in the periodic table, the proton number is a lot lower than the neutron number. Okay, so now you're probably going, well, why? Or I hope you're thinking why. And it's actually quite easy. It's not as horrible as you think it'd be. So the reason we get this greater number of neutrons than protons is because of the protons repelling each other. So we need more neutrons to be able to cancel out those protons repelling each other. So as the number of protons increase, you've got to remember that protons have got to charge and they're going to repel one another. So we need to put something in the way of them repelling one another. So if we can get something there to repel, to stop them from repelling each other, we've got to put more neutrons in. So when you're small nuclei like lithium up here, you're going to have a balancing out. So they're going to be able to balance each other out because there's not a lot of protons. So they don't need to be pushed as far apart because we can have a lower number of neutrons. But if it's bigger and it's got more protons, we're going to need more neutrons to be able to try and stop that repulsion from happening. Okay, so in smaller nuclei, the repulsion's balanced out and the nuclei can be held together by the strong nuclear force. But in larger ones, we need more neutrons to be able to try and cancel it out. Okay, so proton number is a lot lower than the neutron number in anything that's higher in the periodic table. So why? And it's because the protons are repelling each other. So the protons are repelling each other. That's supposed to be a V. However, the protons attract the neutrons, and they're attracting the neutrons, and the neutrons are coming in and they are balancing each other out, and they are creating that binding energy and that strong nuclear force to hold the nuclei together. So this is in smaller atoms, so protons are repelling each other, however protons attract neutrons. So in smaller atoms, the protons and the neutrons basically balance. Just like being in class, I always forget how to spell. So smaller atoms, the protons and neutrons basically balance, but in larger atoms, just checking, you can actually see this on the camera, there we go, but in larger atoms, we need to add extra neutrons. Okay, we add extra neutrons, which don't repel, but they do create an extra attractive force. So basically, by putting in more neutrons, we make sure that those protons stay nice and tightly packed together. All right. So the problem is, the more neutrons that you add, so the greater the amount of neutrons that we start to add, the more unstable the atom starts to become. So eventually, the nucleus just becomes too big, and the bigger it is, the more unstable it is. So eventually, the nucleus becomes too big. And it becomes unstable. So it becomes too big and it becomes unstable. Anything that has an atomic number bigger than 83, and 83 is, if I look at the periodic table on the wall, bismuth. So anything after bismuth is an unstable radioactive nuclei. Now, before bismuth, we've got things like lead, thallium, iridium, osmium, iodine. They are lower than 83, but they still have radioactive isotopes, which we'll talk about a little bit later. So all the elements above, with 83 and above, are unstable and radioactive. Okay, so I'll just include that as well just on the end, and that's the last little bit to this, and then we'll be moving on. So eventually the nucleus becomes too big and unstable, all elements, including and above 83, which is bismuth, unstable and radioactive. Okay, so that means that their nuclei will want to decay, fall apart, and create something stable. So the whole point of radioactive decay is basically to get back to something that is stable and not radioactive anymore. All right, so we can summarize this in two really easy ways. All right, and I'm going to flip this sheet over in a second and I'll write it down. In fact, I'll get another sheet of paper and I'll write it down. So we summarize this in two simple ways, and then when this video is finished, you guys can go back, make your own notes, use my notes that are on here, use the PowerPoint that's going to be uploaded as well, because the PowerPoint is basically this, but I've explained this in a bit more detail. And you can get your own notes down, and there's a couple of questions to answer as well from the notes too. But these are the key things to take from this about why a nucleus would become unstable. Okay, so the two reasons for that are this. I hope you all like my very technical writing board here. So nuclei are unstable if the following things happen. So nuclei are unstable if the proton and neutron ratio is too large, or if it's too small as well. But again, I'll come on to that bit later on. And then the other option is this: if the nuclei is too big for the nuclear force to hold it together. So the nuclei is too large for the nuclear force to hold it's not it together, e.g. bismuth and above. So that one means that if it gets too large, so if the nuclei is too large for the nuclear force to hold it together, so essentially if it starts to get too big, like bismuth is massive, 83 protons, it's got a mass of 209, so that is 126 neutrons. It's absolutely huge, you know, it's the ratio is way too big, and it's just far too big for a force to hold it together. There's just too much going on inside of there for it to be held together, so then it becomes unstable. So they are the reasons why a nuclei will become unstable. So in the next part, the next video that I do, we're going to look at what happens to atoms when they want to become a more stable isotope. So when something that's unstable wants to become stable, it will decay. So we're going to look at the three different types of decay, of radiation, and then you guys are going to do a little task on that in a little bit. So yeah, that's the second video done. Give it a watch through, go back over anything you might need, and yeah, hopefully that was okay. So yeah, there you go, video 2 done.